Welcome to a lesson with Dr. Powell. We're going to take a look at another way of doing the work of pumping water, all the water of a cone, out of it or up to the top in the last method. So this time we're going to compute work, and we're going to do it in the following way. We're going to look at little tiny pieces of the work, but we're going to split it up differently. In the last example, we looked at the force function. We computed what the force function was even, and then we integrated it to find the area in here. Well, we can find the area in a different way. So doing this, thinking of it as f of x dx like we did. What is f of x dx? F of x is kind of like a height times dx times the area of a rectangle. Well, what if we took our rectangles the other way in the picture? We would still, instead of vertically, we do horizontally. We'd still get the same area and we'd still get work. We could take our rectangles going this way. But conceptually, this is nice. This is a nice conceptual way of thinking about it. So let's suppose, for instance, that we're taking position, and we can think in the same kind of light as we did before, and we'll take our position x as being here. Notice that's the same idea as we had before in our picture. X was simply, if we raise this cone upward, we'd have x down here. It just shifted kind of in a picture to get what the cone looks like at the same position. Okay, so now we can think, so we can think about this a little bit in this way. We're going to find the area of that horizontal rectangle. And the way we're going to do that is we're going to take a slab right here, a little piece of the volume. Okay, so we're just kind of thinking of a slab right here. So this is like a little change this is a little change in the force or in the weight, isn't it? I mean, think about the total weight here in this shape. A little volume slab piece right here is like a little change in F. So that would be like a little dF. A little dF would be like this slab of volume. And then think about this right here. Think of that as X. So wouldn't just X times dF equal to that little piece of work? But that should make sense because we're taking a force and we're exerting it over a distance. And if we had a particular force that was constant over a distance, the integral would be very simple. It'd just be the area of a rectangle, right? So it'd be the area of the dF is the height, or is the force, and then x would be over the length of the position. So really the little piece of work, the dW, is really equal to x times dF. Distance this slab has to travel upward times the force of it. So horizontal rectangles are also a nice way to go in this particular case. So let's kind of look at the same problem again. Here are the specs. Okay, we had height of 10 and we had a radius of 2. Now, to compute the volume of the slab, all we really need to know is the radius at this point. We can use what is it, 10 minus x right here. And we notice that the radius will be 1/5 of that height, just like this radius is 1/5 of that height. So we get that the radius again is 1/5 of 10 minus x. And so the area of that circle would be pi times that squared. And then we multiply by a little dx here, change in position, and that'll be the volume of that slab. But that's not quite dF, but if we multiply it by the weight density of water, so 62.3 pounds per cubic foot, and this is in cubic feet because we're multiplying by dx. So the cubic feet would cancel, just have pounds or force. So this would be the total force on that little, given from that little slab that we have to work against from gravity. And then we multiply that by x. And that would give us our little change of work. Then we integrate this as x changes in position from 0 to 10. We evaluate that, and we should get the same work. Now notice this integral looks different than our last one, but we should get the same result. Let's try it, see what happens. Okay, so I should get, taking this out, I should have 62.3 over 25 is my constant coming out this time. Notice the constant that came out last time had an extra 3 in the denominator, so 75. But, and also we have a pi, that's right, pi coming out. Okay, then what's left inside is x times 10 minus x. Right, so x times 10 minus x squared dx. All right, and I'm gonna do a little, for kicks, let's just do a little u substitution. A little u substitution in here. I wanna make this u. So, and so if I make that u, then this thing right here, the reason why I'm doing that is because I want to kind of get this out of the square, out of the square, and I'll show you why. Because if I make this part u, then that means that x would be 10 minus u. And notice 10 minus u isn't squared anymore, so it's a little bit easier to work with. 10 minus u times u. But the derivative of u is -1. So, so I have to divide all this by -1 when I do that in order to change this to du. But then the bounds also change. Okay, so when x is 0, so when x is 0, that means u would be 10. And then 10, then u would be 0. But because I could make this a positive, which would bring me back again to 0 to 10, just like I liked. Okay, that's just sometimes I do things like that in order to help out with my integration. So this would be the integral from 0 to 10, 10 minus u multiplied to u squared du. All right, and then we'll multiply by that constant. Let's see what happens. All right, so this is 10u squared minus u cubed, and take an antiderivative of that would be 10/3 u cubed minus u to the 4th over 4. That's should be a 4. Okay, then we're going from 0 to 10. Okay, we plug in 10 here, and we end up getting 1,000. Oh, 10,000, right? 10,000, sorry. 10,000 over 3 minus 10,000 over 4, which is 25, which is 2,500, right? Yeah, 2,500. So 2,500. Okay. Okay, so 1/4 of 10,000. All right. And then if I multiply this by 3, I get 7,500. Subtract it from 10,000, I end up getting 2,500 on the top again. And then I still have a 3. So really, I just take this and multiply it to that constant, and I should get the work. But if you remember from last time, that's exactly what we had. 3 times 25, we had a 75 in the bottom. Oh, wow, yes, it still works. And then we had 62.3 pi multiplied by 2,500. So it looks so it is the exact same work. We got it by computing it in another way, but it worked both ways. Thanks for watching.